So today we are very happy to have Misha from Berkeley, local, and he'll be telling us about quantum Maximin surface. Please start.
Great. Thanks, Maximin, and thanks for having me here today. So I'm going to tell you guys a little bit about quantum Maximin surfaces. And this is based on a paper that came out in December with Chris Akers, Netta Engelhardt, and Jeff Pennington. So to give a little bit of motivation for what I'll be talking about today, recently there have been significant developments in applying the quantum extremal surface prescription to the black hole information paradox. As an example, the quantum extremal surface prescription gives a unitary boundary page curve, and there's a quantum extremal islands conjecture for calculating entanglement entropies of non-gravitational systems coupled to gravitational systems. So sort of the takeaway from all of this is that we need to better understand quantum extremal surfaces. And the goal of this talk will be to introduce a new tool, the quantum Maximin surface, that will let us prove properties of quantum extremal surfaces that we weren't able to prove before. The overview of the talk will be that we'll go over results in holographic entanglement entropy leading up to the quantum extremal surface prescription. We're going to introduce the quantum Maximin surface and show that it's equal to the minimal quantum extremal surface for some subregion. Then using the quantum Maximin surface, we're going to prove boundary strong subadditivity and entanglement wedge nesting. And then at the end, there will be a couple comments on modifying quantum Maximin to work with non-holographic subsystems. So we'll first start out with a review of holographic entanglement entropy results. So we're going to work within the context of ADS CFT, where you have some boundary and we have some CFT that lives on the boundary, and then we have some bulk with some classical metric for now. And the Ryu-Takayanagi prescription states that the entanglement entropy of some CFT subregion, here R, is given by the area over 4G H bar of a minimal bulk surface. So you find the surface in the bulk with minimal area that is homologous to R, and its area over 4G H bar gives you the entanglement entropy to leading order of the boundary subregion R. One of the constraints on the surface is that it is homologous to R, and what that means is that there's a homology surface H of R such that its boundary is R union XR. And the bulk domain of dependence of this homology surface of H of R is called the entanglement wedge of R. Now, with the RT prescription, there are really simple holographic proofs of boundary strong subadditivity and boundary monogamy of mutual information, along with entanglement wedge nesting. So strong subadditivity and monogamy of mutual information are entropy inequalities, while entanglement wedge nesting is the statement that if we shrink our boundary subregion R, the extremal surface or the minimal surface comes in, and so it's nested inside of the larger, extremal surface. The downside to all of this is that this only applies to static spacetimes where you don't have any interesting time dynamics. But you can extend this to time-dependent bulk spacetimes by the HRT prescription. So the HRT prescription says that now the entanglement entropy of a CFT subregion is given by the area of a minimal bulk extremal surface. So now instead of extremizing, you find, or instead of minimizing, you find the surface that extremizes the area functional, and its area over 4G H bar gives you the entanglement entropy to leading order. Now, extremization is just a statement that the area functional is stationary under surface deformations. So with the HRT prescription, you're no longer restricted to one time slice. So all of the simple holographic proofs we had in RT of strong subadditivity, MMI, and entanglement wedge nesting no longer obviously follow, and you need some kind of modification that will let you prove these statements or see if they fail in some way. And the way that this was done is through the classical Maximin surface. But before we get to the classical Maximin surface, we need to go over a few preliminaries to set up some results. So if you consider a codimension 2 surface sigma, we can deform it along some orthogonal null congruence with null vector k. And we can ask, how does the area of our surface sigma change as we deform it along this null congruence? And this is captured by the classical expansion here. And the sign of the classical expansion tells you whether the area is increasing or decreasing, or maybe it's stationary under a small surface deformation in some direction k. And if you assume the null curvature condition, you have an additional result, which is classical focusing. And this is the statement that the classical expansion is non-increasing as you move along some orthogonal null congruence. And as a final comment, since HRT surfaces are extremal surfaces, since we're extremizing for the area functional, we have that their classical expansions vanish in the two orthogonal null directions. We're also going to need a notion of a representative surface. So if you have some surface sigma, you would like to define a notion of that surface on another Cauchy slice, maybe a Cauchy slice that it doesn't exist on. So the way you can do this is you can shoot out null congruences from sigma. There are 4 directions. And then with an arbitrary Cauchy slice, you can define the representative surfaces on this Cauchy slice as the intersection of these null congruences with the Cauchy slice. So here we fire off null congruences and we get 2 representative surfaces. And for us, we'll always deal with just one representative. So we pick either representative, it doesn't matter in our case. And one important property of representative surfaces is that if our initial surface, sigma, is an extremal surface, its classical expansion is vanishing, then by classical focusing, you have that the area of the original surface is greater than or equal to the area of the representative. And again, this is because classical expansion is non-increasing with the classical focusing theorem. Okay, so now we're ready to get into classical Maximin. But before we do that, let me quickly explain this figure at the bottom. So this is a cross-section of our bulk. And so the vertical direction is time, and then you have slices of Cauchy slices here. And if you cut through a surface, we'll just represent that as a dot. And here, our boundary subregion R is just represented as a dot. So the classical Maximin surface for a boundary subregion R is defined as follows. In the first step, you consider every Cauchy slice such that dr is contained in the Cauchy slice. So here, all the Cauchy slices end on the boundary of R, but they are free to fluctuate elsewhere. And so they don't necessarily have to coincide with R everywhere. Now, on each Cauchy slice, there exists a minimal area surface that we'll call min sigma, that is homologous to R. So you take all of these minimal area surfaces, min sigma, and from them you take the maximum area surface. And that is defined to be the Maximin surface M of R. So in this figure, sort of these green surfaces correspond to minimal area surfaces homologous to R on their respective Cauchy slices. And the Maximin surface is also a minimal area surface homologous to R, but it's the one with maximal area. So this red surface has larger area than these green surfaces, and it has larger area than every possible green surface. Now, as a quick corollary to this, by construction, we know that the Maximin surface is the minimal area surface homologous to R on one Cauchy slice that we'll call C of MR. Okay, so that's the definition of a classical Maximin surface. And for now, we won't get into whether it exists. We'll come back to that a bit later when we talk about existence of the quantum Maximin surface. Right, but given the definition of the classical Maximin surface, what we can do is we can show that the Maximin surface M of R is equal to the HRT surface. And to show this, we need to show two properties. One, we need to show that the classical Maximin surface is extremal, and we need to show that it's the minimal area extremal surface. So to show that it's extremal, the intuition is pretty simple. So by construction, the Maximin surface is the minimal area surface on its own Cauchy slice. And so you can vary it on that Cauchy slice. And its area will be stationary. And so it's extremal in at least one direction. And then it's maximal with respect to variations of the Cauchy slice. And so you have that it's extremal in a second direction. And so since it's extremal in two directions, it is an extremal surface. Now, to show that the Maximin is the minimal area extremal surface, to show that it's the HRT surface, we can argue by contradiction. So we can say, suppose that it isn't the HRT surface. Suppose there's another HRT surface, X of R, with smaller area than the Maximin surface. Well, what we can do is we can send out a null congruence from the HRT surface that hits this C of MR Cauchy slice. And by classical focusing, we know that the area of the HRT surface has to be greater than the area of its representative. Now, because the Maximin surface is the minimal area surface homologous to R on its Cauchy slice, it has to have smaller area than this representative. And so that's where you get the second inequality. And so through this argument, you can sort of see that in the worst case scenario, the Maximin has just as much area as the HRT surface. So it itself is an HRT surface. So we've reached a contradiction. So this proves that the Maximin surface is an HRT surface. And you can use these kinds of arguments to prove boundary strong subadditivity, MMI, and entanglement wedge nesting for HRT surfaces. You basically use representatives to put every surface that you're interested in on one Cauchy slice, and then you use inequality type arguments to prove these statements. And we'll get into these when we prove these properties for quantum Maximin surfaces.
Misha?
Yes.
Can you remind me how to think about the possibility that, for example, the representative of XR on C is just the empty set? Or, I mean, there's presumably some homology condition here that needs to be satisfied between the representative and MR?
So the representative surface, so X of R is homologous to R. And so the representative surface is also homologous to R. But are you asking whether a representative exists?
Well, so when I consider the future, say the light rays coming out in some direction out of some surface, for example, if I take a sphere in Minkowski space and I take the light rays going towards the inside of the sphere, eventually they just, all focus and the null surface ends there, and any later Cauchy slice won't be intersected by them. I'm confused about that situation and how that relates to this construction, although I'm supposed to know that, but I forgot.
Right, that's exactly right. So generically, you can have either 2 representatives, 1 representative, or 0 representatives. So in our case here, we use the fact that the causal wedge is contained in the entanglement wedge. And so there will always be a representative of X of R that hits CMR, because C of MR has to end on the endpoints of R. Does that answer the question?
It helps. I think I can think the rest through. Yeah.
Okay. So everything we've done so far has been with just area, but let's move beyond that. So the Engelhardt-Wall prescription states that if you want to calculate the entanglement entropy of some boundary subregion R, then what you should do is you should extremize the generalized entropy. So instead of extremizing the area functional, you now extremize the generalized entropy functional under the same homology constraint that you had in the case of area. So what is the generalized entropy? Well, the generalized entropy can be split into 2 parts. It can be split into a gravitational part, and it can be split into a von Neumann entropy part. So the gravitational part of the generalized entropy at leading order, it's just the area of the surface over 4G. And then there are additional local geometric terms like extrinsic curvatures that I'll mention in a few slides. And the von Neumann entropy is calculated for the bulk fields in your homology surface H of R. So there are some fields in your bulk, and if you restrict them to this homology surface, they have some density matrix, and you just calculate minus trace rho log rho of this density matrix, and that gives you the von Neumann entropy. So the claim is that you extremize this functional of these 2 terms added together. Now the gravitational terms are all local. They're like areas of extrinsic curvatures, as I stated, but the von Neumann entropy is non-local. You can imagine, qubits that are entangled across this surface. And by slightly deforming the surface, you might change the generalized entropy in a non-local way. This is conjectured to be true. This prescription is conjectured to be true to all orders in H-bar. And here again, we run into the same problem that we had with HRT surfaces. So since you're extremizing this functional, quantum extremal surfaces are not confined to 1 time slice. So how do we prove SSA and entanglement wedge nesting? Or are they even true? So how you prove them is with quantum Maximin surfaces. And again, for quantum Maximin surfaces, we're going to need some preliminary tools before we get started. So
Sure.
we're going to need to promote certain
Misha,
classical. Sorry, yes?
Could you just clarify, before we worry, so there's sort of 2 things, right? One is going from the static to the dynamical case, with like RT to HRT, and one is going from classical to quantum. Are you saying, suppose we stayed with the static case, but we went from classical to quantum, would proving things like strong subadditivity and entanglement wedge nesting and so on be trivial at the quantum level in that case?
It would be easier, a lot easier, because everything is already on 1 time slice. So you'll still need like bulk strong subadditivity to prove strong subadditivity, but you don't need the representative technology.
Yeah, I can see how it works for strong subadditivity. Yeah, so you're basically saying all the arguments from the classical case just go through completely unchanged in that case.
Yes.
Thanks.
Okay. So in preparation for quantum Maximin, we'll need to promote certain statements to their quantum generalizations. So we're going to send the area over 4G H bar to the generalized entropy. And we're going to send the classical expansion to the quantum expansion. Now, as a reminder, the classical expansion sort of told you how the area of your surface changed if you deformed it a little bit along some null vector. And the quantum expansion sort of tells you how the generalized entropy changes as you deform your surface along some null direction, k. And we're going to send classical focusing to the quantum focusing conjecture. So this is the conjecture that the quantum expansion is non-increasing. And an additional comment, so again, since we're extremizing the generalized entropy, quantum extremal surfaces satisfy that capital theta k is equal to capital theta L is equal to 0. They're stationary under deformation. So the QFC has an interesting consequence for quantum extremal surfaces. Let's say you start with an initial surface sigma that has vanishing quantum expansion along some null direction k. If you find its representative on some later slice, this sigma tilde, by the QFC, you know that the generalized entropy of the representative has to decrease. This is a consequence of quantum focusing. You can see that this is a generalization of classical focusing. And we're also going to need to comment on these gravitational terms. So the gravitational functional comes from the action that you choose to work with. So if we have some higher curvature action like this, where lambda 1 and lambda 2 are dimensionless coupling constants of order 1, and L squared is the string length squared, then the gravitational functional you get is something like this. You have the area over 4G H bar out front, and then you have an integral over your surface with some Riemann terms and some extrinsic curvature terms contracted with a normal projector. These extrinsic curvature terms will be important for us later. So there are going to be a few situations where our surfaces are going to have corners, and the extrinsic curvature isn't well defined for such surfaces. So we're going to have to handle this by smoothing out the corners at a scale above the Planck scale, but below the bulk field theory scale. So the excitations in the bulk are characterized by the bulk field theory scale. So smoothing corners at a scale below this scale will not change the von Neumann entropy very much, but the area will decrease with smooth corners, and the area term will dominate over all these higher order terms. And so overall, S grav will slightly decrease with smoothed corners, and so S gen will decrease with smoothed corners. Okay, so now we're ready to jump into quantum Maximin. So given a boundary subregion R, the quantum Maximin surface is defined analogously to the classical Maximin surface. So here, as the first step, we'll consider all Cauchy slices such that the full boundary subregion R is contained in the Cauchy slice. I should comment on this. The reason we strengthen this definition is because we wanted to deal with cases where maybe the bulk was coupled to some auxiliary quantum system, and degrees of freedom were allowed to escape the bulk and enter some auxiliary system. But this can actually be relaxed to be the direct analog of the classical Maximin case. But we'll keep it to be this for our case, because it makes some things easier.
Misha?
Yes.
Would it actually make a difference? Like if you had insisted, like, yeah, would you get a different Maximin surface either in the classical or in the quantum case, depending on whether or not you insist that all of R be included in sigma?
No, at least not. Maybe in situations where you have certain types of singularities, they would differ. But generically, not really, no. Okay. So again, on each Cauchy slice, there exists a minimal generalized entropy surface that we'll again call min sigma, that is homologous to R. And we again take the set of minimal generalized entropy surfaces, and from it we take the maximal SGen surface. So here again, maybe on this Cauchy slice sigma, we have this minimal SGen surface. And on this Cauchy slice Cm of R, we have this min SGen surface. The same thing here. And the Maximin surface has larger generalized entropy than all these other minimal generalized entropy surfaces. And as a corollary or as a reminder, just by construction, this Maximin surface M of R is the minimal SGen surface on this Cauchy slice Cm of R. This is really important for the proofs we're going to go through. So we've defined these Maximin surfaces, but you can ask, are they even well defined? Do they exist? And for that, you have to answer two questions. The first question is does a minimum generalized entropy surface exist on a given Cauchy slice? And the second question is whether the maximization procedure we've outlined is well defined. So let's first talk about the minimization procedure. So the classical argument for this was that the set of all surfaces homologous to R on some Cauchy slice is compact. And if the area functional is lower semi-continuous on the space of surfaces, then a minimal area surface exists. So we'd like to ask, is generalized entropy lower semi-continuous? So a functional is lower semi-continuous if a small surface deformation can't arbitrarily decrease the value of the functional, for example, the area. So for the area, if you take some initial surface and you do a small deformation to your initial surface, then you can arbitrarily increase the area, but you can't arbitrarily decrease the area. And so area is a lower semi-continuous functional, and this was the argument for why a minimal area surface exists. Now, for the generalized entropy, we can't be as mathematically rigorous because the bulk entropy contributions are non-local, but we can try to see if the gravitational piece, at least, is lower semi-continuous. And this is where these extrinsic curvature terms become important. So you can sort of see that if these extrinsic curvature terms approach 1 over L squared, then these terms that were supposed to be subleading are now competing with the area contribution. And naively, if you're minimizing over all surfaces, then minimization will favor a surface with arbitrary large extrinsic curvatures. And you can actually construct explicit examples where the gravitational entropy is negative. So generically, we should actually include all higher curvature terms in our action. And so this functional will be some kind of series. And when we're thinking about surfaces that approach, it's 1 over L squared, extrinsic curvatures that approach, 1 over L squared, the entire series will start to diverge. And the problem is really that these surfaces are in a sense beyond the validity of effective field theory. And you shouldn't really be asking about these sorts of questions. So we'll take the point of view that within some maybe smaller class of surfaces, maybe where all extrinsic curvatures are a lot smaller than this L squared, that a minimal generalized entropy surface exists. But we can't prove it. And by the way, this sort of problem was also sort of there in the classical case where on one hand you said that you're dealing with classical general relativity, but on the other hand, you were minimizing over surfaces with arbitrarily large extrinsic curvatures. And you might wonder, is this really something that should be allowed and should be well defined? But we'll have to assume that a minimal generalized entropy surface exists. So the second step that we need for the Maximin procedure to be well defined is for the maximization over Cauchy slices to be well defined. And the classical argument is very similar. The set of all Cauchy slices is compact. The area of the minimal surface on a Cauchy slice is upper semi-continuous. And therefore, the maximization converges and is well defined. For quantum Maximin, the story is kind of similar, so I won't really get into it. You can believe me that the maximization also works out. Right. So now that we have that the quantum Maximin surface exists, we can show that it's an extremal surface. So on its Cauchy slice, we can infinitesimally deform the Maximin surface along some vector n. And because it's the minimal S-gen surface, this deformation has to increase the generalized entropy. And so you can sort of sandwich the inequality like this to show that it's extremal on the Cauchy slice. Now, you can also deform it in a timeless.
Misha, sorry. Yeah, there's the part where you talked about existence went a little fast for me. So you were concerned separately about varying on a Cauchy surface and then later varying the Cauchy surfaces. And did I understand correctly that you think you have a rigorous argument for the latter, but not for the former?
I would say we don't have a rigorous argument for either.
You seem more comfortable about the latter, but maybe I misread that.
Yeah, I would say we don't have a rigorous argument for either, unfortunately.
So existence is an assumption in both respects.
Yes.
Okay, thanks.
Right. But getting back to extremality, so we can vary the surface on the Cauchy slice and show that it's extremal in one direction, and we can sort of vary it in time to a nearby minimal S-gen surface on a different Cauchy slice and show that it's extremal in a second direction. So because it's extremal in two directions, it's an extremal surface. And similar to the classical Maximin argument, we can show that the quantum Maximin surface is the minimal S-gen quantum extremal surface. And the way we're going to do this is that we're going to argue by contradiction. We're going to assume that the Maximin isn't equal to the minimal quantum extremal surface. So we're going to assume we have some x of r here with smaller S-gen. And we're going to shoot out a null congruence and find its representative on C m of r, on the Cauchy slice on which m of r is minimal. Now, by quantum focusing, we have that the generalized entropy of the representative is smaller than the generalized entropy of the original quantum extremal surface. And because by definition, M of R is the minimal S-gen surface on its Cauchy slice, we know that the S-gen of M of R has to be less than the S-gen of the representative. And so from this, we again see that in the worst case scenario, the Maximin has as much generalized entropy as the minimal quantum extremal surface. And so it's just as good as the minimal quantum extremal surface. So M of R is a minimal quantum extremal surface. Okay, so now that we know that M of R is equivalent to the minimal quantum extremal surface, we can go ahead and prove strong subadditivity and entanglement wedge nesting. The power of Maximin really comes from these three properties, that it's equivalent to the minimal quantum extremal surface, and that it's the minimal generalized entropy surface on its Cauchy slice, and also using representative techniques with the quantum focusing conjecture. So using quantum Maximin, our sort of method of proof will be to take dynamical setups and place them on one Cauchy slice, and then apply cut and paste techniques that were applicable in the static case. So we're going to start off with entanglement wedge nesting. So the statement of entanglement wedge nesting is, let's say you have some subregion R2 and subregion R1 is contained within R2. And you have Maximin surfaces MR1 and MR2, and these homology surfaces HR1 and HR2. The statement of entanglement wedge nesting is that the domain of dependence of HR1 is contained within the domain of dependence of HR2. And we're also going to show that the Maximin surfaces MR1 and MR2 are minimal on the same Cauchy slice. Now, the way we're going to prove this is as follows. So the first step is that we're going to maxi-minimize for the quantity S-gen M1 plus S-gen M2. So what this means is we're going to consider all Cauchy slices that end on R2, that contain R2. And on each of those Cauchy slices, we're going to find two surfaces that minimize this quantity. And so we're going to do this for every Cauchy slice. And then from that set of surfaces, we're going to take the set of surfaces that maximize S-gen M1 plus S-gen of M2. So the end result of this maxi-minimization is we'll get two surfaces, M1 and M2, on a Cauchy slice. And we know that their S-gens, the sum of their S-gens is minimal. And what I mean by that is that if you pick any other two surfaces or any other pair of surfaces on that Cauchy slice that are homologous to R1 and R2, they'll have larger S-gens. So what we're going to show is that this procedure gets us surfaces that are equivalent to MR1 and MR2, and that these homology surfaces, H1, nest in H2. And this will imply entanglement wedge nesting. So after maxi-minimizing, we get two surfaces, M1 and M2, on the same Cauchy slice. Now at this point, we don't know if they're extremal surfaces. We just know that after we maxi-minimized the sum of their generalized entropies, this is what we got in the end. So first, we're going to argue that their homology surfaces nest. And to do that, we're going to start off arguing by contradiction. We're going to say, let's assume that they don't nest. What we're going to do is we're going to construct two surfaces here that are homologous to R1 and R2, which have smaller S-gens than the sum of S gen M1 plus S gen M2. And this will be a contradiction, and this will tell us that H1 is not a subset of H2. Okay, so we define these prime surfaces as follows. So this M1 prime surface is sort of this purple region, and then the M2 prime surface is the entire exterior. And what we want to show is that S gen of M1 prime plus S gen of M2 prime is smaller than S gen of M1 plus S gen of M2. And what we can do is we can expand S gen on each side here to be a sum of gravitational entropies and von Neumann entropies. And if we show that this holds for the gravitational and for the von Neumann entropies, then we've shown this inequality. So the von Neumann entropy inequality is just bulk strong subadditivity. The von Neumann entropy of H1 is just the von Neumann entropy of the purple region and the blue region, while the von Neumann entropy of H2 is the von Neumann entropy of the two red regions and the purple region. The von Neumann entropy of H1 prime is just the von Neumann entropy of the purple region, and the von Neumann entropy of H2 prime is the von Neumann entropy of all of these four regions. Great.
Could you say what H1 prime is?
Yeah, sorry. So M1 prime is this purple region in here. And H1 prime is, well, I guess H1 prime is the purple region, and M1 prime is its boundary. Right. And the other...
not being fast enough, but is it clear that the divergences in the von Neumann entropy are the same on the left and right side?
The divergences.
So those cancel?
Let me see. Area. Yes, I believe to leading order, you'd pick up like an area here, and then the area divergence here for the prime surfaces, and for the unprimed surfaces, you'd pick up the area divergence out here, and then also here. So each boundary is only picked up once.
Yeah, but what about the corners in some of these new regions?
Yeah. So unfortunately, the way we're going to deal with corners is we're going to smooth them out, as I previously mentioned. And our argument is that the von Neumann entropy doesn't change that much if you sort of smooth them out at a length scale much shorter than the bulk EFT scale.
So the corner contributions don't necessarily cancel, but you can argue that they're negligible.
Yeah, exactly. Okay, so we have these von Neumann entropy inequalities, and now we need to show this gravitational entropy inequality. So again, the gravitational term just consists of local geometric terms confined to the surface. So if we just cut up these surfaces into these prime surfaces, away from the corners, all the contributions are exactly the same. So the only new contributions come from the corners. And again, what we're going to do is we're going to smooth these corners out a little bit, such that the area will decrease and all the higher order terms will be subleading to the area. And in this way, the gravitational entropy of the primed surfaces with smoothed out corners will be strictly less than the gravitational entropy of the initial surfaces we started with. And so we can add these two inequalities to get this final inequality, that the S gen of M1 plus M2 is greater than the S gen of the M1 prime surface plus the M2 prime surface. And by construction, this contradicts the minimality of S-gen M1 plus S-gen M2. And so we must have that these surfaces actually nest. We must have that H1 is a subset of H2. Okay, so we have that these surfaces M1 and M2 are nested in the appropriate way, but we need to prove that they are equal to the Maximin surfaces MR1 and MR2. And the way you can do this is that since the surfaces don't intersect, you can independently vary them at all points to show that they are extremal. Okay, so once you have that they are extremal, you can use the representative argument we presented earlier to argue that these are actually the minimal extremal surfaces. And so in this way, you can show that M1 and M2 are equal to MR1 and MR2. And since we already showed that H1 nests in H2, we've proven entanglement wedge nesting. A separate core. Sorry, was there a question? A separate corollary is that if there are a set of disjoint regions, Ri, we can maxi-minimize for this quantity where you add up all these S-gens, and the resulting surfaces Mi are the corresponding minimal quantum extremal surfaces for these regions. So the power of this is that you can place the quantum extremal surfaces for a bunch of regions on just one Cauchy slice. Okay, now that we've proved entanglement wedge nesting, we can prove strong subadditivity for boundary regions R1, R2, and R3. So we want to prove this inequality, that S-gen of M12 plus S-gen of M23 is greater than or equal to S-gen of M123 plus S-gen of M2. So how we do this is first, we maxi-minimize for the quantity S-gen M123 plus S-gen M2. Now, because R2 is nested within regions 1, 2, 3, we find that these Maximin surfaces live on the same Cauchy slice by entanglement wedge nesting. And so in this figure, you see you have M2 and M123 on the same Cauchy slice on which their sum is minimal, on which their sum is smaller than any other two surfaces that you can choose homologous to 1, 2, 3, and to 2. However, M12 and M23 don't necessarily have to live on this Cauchy slice. They can be somewhere else. And so what we're going to have to do is we're going to have to send out a null congruence to intersect this Cauchy slice to give us these representative surfaces, M tildes. And so again, we know by quantum focusing that the generalized entropy of a representative decreases if the starting surface is a quantum extremal surface. So we have that S-gen of M12 plus the S-gen of M23 is greater than or equal to the S-gen of these M tilde surfaces. So now the setup we have is something like this. You have M123 and M2, and then the two tilde surfaces all on the same Cauchy slice. And we're going to apply the cut and paste arguments that you can apply to the RT prescription. So what we're going to do is we're going to cut apart these tilde surfaces to give us these prime surfaces. So these prime surfaces are homologous to regions 1, 2, 3, and region 2. So the way you cut them is you take one surface to be this segment, and you take the other surface to be this segment and this segment. Now, similar to the proof of entanglement wedge nesting, you can argue that the von Neumann entropy satisfies this inequality. You use bulk strong subadditivity. And then by smoothing the corners, you argue that the gravitational entropy of these primed surfaces is smaller than the original green and blue surfaces you started with. So you end up with a statement that the generalized entropy of the M tilde surfaces is greater than the generalized entropy of the primed surfaces. Okay. But now these primed surfaces are homologous to regions 1, 2, 3, and to region 2. So by the minimality of the maximin for 1, 2, 3, and for the maximin for 2, we must have that these primed surfaces have larger generalized entropy. Okay. And now you stitch together these three inequalities that we've proven, and you get that boundary strong subadditivity holds. Sgen of M12 plus Sgen M23 is greater than or equal to the Sgen of M123 plus the Sgen of M2. So for monogamy of mutual information, the story is a little bit different. This is an entropy inequality that doesn't hold for general quantum states, but for HRT surfaces, you can use classical Maximin to prove it with cut and paste techniques. But quantum Maximin surfaces violated at next to leading order. And for boundary MMI to be true for quantum Maximin surfaces, you need a 7-party bulk inequality, which does not necessarily have to be true. Okay. So as I mentioned earlier, there's been interest in applying the quantum extremal surface prescription to situations with non-holographic systems. So the way this is typically done is that you're given a boundary subregion R and some non-holographic system Q. And what you do is you extremize this functional that sort of looks like a generalized entropy to find a quantum extremal surface for your system R union Q. So now you extremize over all surfaces in the bulk, homologous to R, and you extremize for the sum of the gravitational entropy of the surface, plus the von Neumann entropy of your homology surface, same as before, union your auxiliary quantum system Q. So this is a little bit different from the generalized entropy. And we say the surface that extremizes this quantity is called, the hybrid quantum extremal surface. So if this is to compute an actual entanglement entropy, it should satisfy some properties. And we can sort of prove that this hybrid entropy satisfies an analog of strong subadditivity and entanglement wedge nesting by reformulating this in a modified quantum Maximin language. So we can extend a quantum Maximin to sort of accommodate this auxiliary system Q with a given boundary subregion R by now, when we do the minimization step, we minimize for the hybrid entropy instead of the generalized entropy. And then after we do the minimization, we maximize over all of Cauchy slices to find the modified quantum Maximin surface. Now, the way to think about proving existence and equivalence and extremality of these modified Maximin surfaces is as follows. You can take your auxiliary quantum system Q and you can throw it into a separate holographic bulk. And then the hybrid entropy just reduces to a generalized entropy of your original bulk theory and the empty surface in the auxiliary bulk. So Right. And now this turns into, a maxi-minimizing of a generalized entropy. And using this technology, you can prove entanglement wedge nesting and strong subadditivity for the modified quantum Maximin surface, and I guess for the hybrid entropy extremal surfaces. So as an example of how this goes, it's very similar to the proofs we already went over. So as an example, for entanglement wedge nesting, you have some subregion R1 nested in R2, and you have some auxiliary quantum system Q1 contained within Q2. And we can maxi-minimize for the hybrid entropies of both of these systems. And we go through the same argument where we assume that they don't nest, and we set up a contradiction. And the only thing that changes here is that now the von Neumann entropy inequalities include these auxiliary quantum systems Q1 and Q2. And so you also need to assume that these auxiliary quantum systems satisfy strong subadditivity. But the same arguments go through, and you can show entanglement wedge nesting and also, again, strong subadditivity of the hybrid entropy. So a summary of what we've done in this talk is that we've shown that the quantum Maximin surface is equal to the minimal S-gen quantum extremal surface. We've proven entanglement wedge nesting and boundary strong subadditivity for the Engelhardt-Wall prescription. And we've extended the quantum Maximin construction to accommodate auxiliary, non-holographic subsystems. And we've shown that the hybrid entropy satisfies an analog of entanglement wedge nesting and strong subadditivity. So some possible future directions could be, well, the Maximin prescription is very general. So can it be adapted to maybe some other contexts where you're interested in minimizing some quantity or maximizing some quantity? And as a second question, in the construction, we had to consider the generalized entropy of arbitrary surfaces. So does this generalized entropy have some kind of interpretation? And what does it mean for a surface to have minimal generalized entropy on some Cauchy slice, if there is such an interpretation? Thank you.
Thanks, Misha.
We still need a better system for clapping, but
yeah, there's actually a little button for clapping on the chat thing. So like you can do this if you're looking at the participant thing. It indicates you're clapping.
Yeah, I would say there's room for improvement on that front. All right, any other questions for Misha? Okay, if not, let's try Ning's method for clapping.
Yeah.
but it makes no noise though, right? It just appears. Yeah. It's very good. Thank you, Misha.
Thank you, Misha.